On clear moonless night, away from the city lights, when we look up, we see several stars, millions of them. Among this, we also see a diffuse band running across the sky. That what we call as our own galaxy, to which our solar system belongs, the Milky Way, Akash Ganga. Over the years, we have discovered billions of galaxies like our own beyond our own galaxy. These galaxies are the building blocks of the universe, and therefore studying them as a population as well as individual is very important for studying the overall structure of the universe as a whole. To begin with, let us ask, what is a galaxy? A galaxy typically consists of few billions of stars like our own sun. These galaxies occur in varieties of shapes, sizes, masses. Some look like elliptical on photographic image. Some have beautiful spiral arms and disks. Way back in 1926, Hubble arranged them in a sequence, what we call as Hubble sequence of galaxies, ellipticals, lenticulars, and spirals. The question which has been puzzling since then, is there any unity in the diversity of variety of galaxies? How do galaxies form? How they evolve? And how all these varieties of galaxies play a role in the dynamics of the universe? Today, we have with us Professor Richard Ellis from Caltech, United States of America. He is an expert on galaxies, studying various aspects of galactic structure, probing at very, very high rate shifts, which will all be important for studying the structure and evolution of the universe as a whole. We will know more about the galaxies with the advent of newer technologies, new telescopes, ground-based spaceborne. See, with the discovery of first galaxies, which we call as nebulae, we have come a long way discovering newer and newer galaxies, varieties of them. Common men often ask questions when we talk about bigger and bigger telescopes, spaceborne telescopes, right? We talk about gamma ray astronomy, talk about X-ray astronomy. The question which often we ask is, why do you need bigger and bigger telescopes? Why do you need X-ray telescope, for example? Why do you need gamma ray telescope? Why do you need radio telescopes? So, could you please?
Sure. Well, galaxies are complex objects. As you mentioned in your introduction, they come in a variety of sizes and shapes. And when Hubble classified them, this was what we call a morphological classification. It's a taxonomic scheme that doesn't necessarily have any physical principle behind it. He took optical photographs of galaxies and then categorized the galaxies according to their forms. But he was a very intuitive observer, and it turns out that the Hubble classification scheme, the one that he developed in 1926, is still the one that we use today. And the reason for that is that it bears a strong relation to the physical differences of galaxies. So at one end of the sequence, the elliptical galaxies are very simple structures. They are spheroidal in form. They're either spheres or ellipsoids. They don't have any young stars or spiral arms. They contain mostly old stars. And so it's been thought for many years that they're relatively old systems that formed a long, long time ago. The spiral galaxies, on the other hand, have a lot of young stars and are rotating much more rapidly than the ellipticals. They're dynamically very different. They have a disk, and that disk is rotating, like in our own Milky Way galaxy. And so dynamically, they're a very different object from the elliptical galaxies. When we started having the technology for looking at galaxies with X-ray telescopes and with infrared telescopes, we found that the scheme had to be expanded to cover galaxies that are luminous at other wavelengths other than the optical. So for example, an infrared galaxy is a galaxy that has a lot of dust in it. That dust is heated by young stars and radiates in the infrared, where the dust is warmed up by the young stars in the galaxy. X-ray wavelengths are sensitive to the very hottest stars. So if a galaxy is particularly energetic, it will be seen in X-rays. So the key question now is, where do all these different types of galaxies come from? How do they relate to one another? And the work that I do is concerned with looking at galaxies as they were a long time ago. And a big telescope has the capability, of course, of seeing fainter objects. The reason we're interested in building more powerful telescopes is that they're capable of detecting signals from remote parts of the universe. Now, why do we want to study distant parts of the universe when there are galaxies nearby that we could study much more easily? And the answer is that when we look to great distances in the universe is so large that the light rays have been taking an appreciable fraction of the age of the universe to reach us. So when we look deep in the universe, we're effectively looking back in time. And the further we look, the fainter we look, the further back in time we look. So we can't study the evolution of one galaxy in any detail, but what we can do is look at the universe in different time slices and attempt to reconstruct, by inference, the evolution of galaxies. And of course, the more powerful the telescope, or the higher the resolution of the telescope, the better information we get on distant parts of the universe, and hence on the universe when it was very young.
So, see, you talked about the evolution of galaxies. See, astronomers are pretty sure about how stars evolve, how they form, and how they die. Likewise, one may ask basic question about the galaxies. How galaxies are formed, or rather when are they formed, how they evolve. Do the Hubble sequence tell us something about the evolutionary sequence of the galaxies?
Right.
Could you
yes.
please?
Well, you're right that stellar evolution in the 1920s and 1930s was a breakthrough in astronomy, and we now have a very clear idea of why we see such a variety of stars of different temperatures and luminosities. And we learn that stars actually evolve from one kind of star to another.
Yes.
And this beautiful pattern of stellar evolution is one of the triumphs of 20th century physics. We would now like to get to the same level of detail in galaxies, but there are some stumbling blocks along the way. It doesn't follow by analogy that we can develop the same technologies and approaches. But the answer is yes. When people first started looking at galaxies of different types, as I already mentioned, the ellipticals contain mostly old stars, and the stars are red in color. The galaxies are relatively compact and simple in form, and so it was natural to assume that these were the first galaxies that formed, and that they collapsed at some time in the distant past as a single event, what we call monolithic collapse. And so my colleagues and I have been trying to find out whether there is an era in the distant universe when the elliptical galaxies formed in this way. The spiral galaxies, however, contain young stars. Those young stars are an indication that the galaxy is still forming stars and that it's very much an active system. And in that case, a galaxy like a spiral galaxy formed more gradually over time. Maybe it collapsed by a larger amount so that any small rotation that galaxy has is amplified as the disk collapses into a plane. And so in this way, a very simple picture in the 1970s was built up, explaining the different Hubble sequence in terms of the rate at which the stars formed in a galaxy. Unfortunately, we think that sequence is too simplistic. And the reason for that is we now believe that the universe contains quite a bit of dark matter in addition to the shining stars that we see with our telescopes. And this dark matter seems to play a key role in the building up of galaxies. We now think that galaxies build up not as single entities, but from subunits, from smaller systems. And it's this merging of smaller systems into bigger systems that is the way in which galaxies assemble. And for example, it may be that two spiral galaxies could exist and merge together to form an elliptical galaxy.
Do you have some evidence in support of?
And we have evidence that mergers do occur and that spiral galaxies do bump into each other. And the numerical models suggest that when two spiral galaxies collide, their disks are destroyed, the gas is converted into stars, and the product may very much look like an elliptical galaxy. Now, this doesn't mean that all elliptical galaxies were formed by mergers, but it leads to a complication that at the Hubble sequence, a galaxy may change its position on the Hubble sequence depending on where it is in its environment. So, trying to unravel how we get from the universe at one period to another is turning out to be more complicated than we thought. But of course, we have the tools to do it, and if the samples are big enough, then we have the way forward in trying to understand the answer to that question.
In addition to what we call as normal galaxies, right, which we have classified, there are bizarre objects, quasars, quasi-stellar objects, Seyfert galaxies, in general called elliptic nuclei.
Right.
Where do this bizarre objects fit into the the system of galaxies?
Well, 99% of galaxies are normal in the sense that they can fit into Hubble's classification scheme. 1 or 2% of the galaxies are either totally peculiar in their shape, or they have a luminous source in their center, which we call an active nucleus. And it may well be that all galaxies go through a phase where they have an active nucleus. For the nearby galaxies that can be studied in detail, we now know, including our own Milky Way, we now know that there are massive black holes in the centers of these galaxies. This is a triumph in our own galaxy. The motions of stars in the center of the galaxy have been analyzed very carefully, and the dynamics indicates unambiguously that there is a black hole of several million solar masses in the center.
Including our own galaxy.
Including our own galaxy. Now, what happens when material is drawn inexorably into this black hole is that it's heated up. And this radiation that emerges from the black hole as the material is falling towards the black hole is a very luminous source of energy. And so long as the gas is falling towards the black hole, this nucleus will shine very luminously. However, it's possible for this flow of gas to be erratic and be interrupted. And one of the challenges is to try to understand what switches on this phenomenon and what does not. But it looks like every galaxy may have some component of activity at some time in its life.
Right. You talked about bigger telescopes which help us to probe the universe deeper in time. In the process, do we hope to sometime in near future to detect what we call as first galaxies?
Right.
And what is the role of giant meter radio telescope that Pune has in discovering such primordial galaxies?
So finding the very first galaxies is the hottest topic at the moment in cosmology, and a driver for making big telescopes. We think the universe is about 14 billion years old, and with our current telescopes, we can look back to when the universe was about 1.5 billion years old. So that's about 90% of the way back to the Big Bang. And so far as we can survey the universe to this period when it was 10% of its present age, there are still galaxies in abundance. They seem to be a little bit smaller than present-day galaxies. They're more active, they're forming stars more ferociously than the present-day population, and they don't have regular forms. And the most important instrument in determining these results has been Hubble Space Telescope. Hubble has taken extraordinarily deep images of very small areas of sky,
Right.
and giant ground-based telescopes of various wavelengths, radio and optical and infrared, have studied these areas that Hubble has imaged and tried to understand the relative distances of all of the galaxies. And it looks like out to about 90% of the way back to the Big Bang, the galaxies are still present. Now, beyond this, we have two problems. Firstly, the universe is expanding. And what this means is that radiation is shifted to longer wavelengths. So an optical telescope is not particularly efficient for studying the most distant objects, where the radiation is strongly redshifted into the infrared. So one of the big problems is we wait for the successor to Hubble Space Telescope, the James Webb Space Telescope, which is primarily an infrared telescope, which will give us a glimpse of the universe at even earlier times. Now, the radio telescope, the GMRT, is particularly powerful because it can study neutral hydrogen at very, very early times. Now, we think hydrogen is the key component. And molecular hydrogen in particular, in the cooling of this hydrogen, is the mechanism by which the very first stellar systems can form. So another probe of the very earliest times will be to try to identify features in redshifted hydrogen for which the GMRT nearby here in Pune, is very, very likely to be powerful. Now, what do we do while we wait for these experiments? One possibility is to try to characterize the very earliest systems by hydrogen that we can see at optical wavelengths. There is one signature of hydrogen, which we call the Lyman alpha line, which is the recombination line of hydrogen to the ground state, which tells us the abundance of hydrogen and its temperature at early times. And so one of the exciting developments is searching for this signature of neutral hydrogen at very early times using spectrographs on big telescopes. But this is very demanding, takes a lot of effort, even with the very, very biggest telescopes.
These galaxies, besides occurring in isolation, they occur in other structures, what are clusters of galaxies, clusters of galaxies.
Right.
So what is the role of this bigger structures and how this bigger structures forms? What is their role in the cosmological?
So the galaxies themselves can be regarded as tracers of bigger structures. And as you said, what we find is that it's dangerous to think of galaxies evolving in isolation. They're part of a much bigger structure. Galaxies are found in clusters and filaments and structures. And very recently, some very extensive surveys have been done with ground-based telescopes to catalog the spatial distribution, in one case of over 100,000 galaxies. And we see a rich tapestry of structure that galaxies belong to filaments, large-scale structures, and so forth. Now, we think this is a manifestation of the role of gravity in building up galaxies and their large-scale structures. And numerical calculations suggest that the dark matter picture can give a very accurate description of this large-scale structure. But as far as the evolution of galaxies is concerned, it has another role, and that is that galaxies do tend to depend on their environment. So, for instance, if we go to the densest region where there's the largest number of galaxies per unit volume, we find that the fraction of galaxies that are elliptical is very high, and the fraction of galaxies that are spiral is very low. Whereas if we go out of clusters into low-density regions, most of the galaxies are spiral. So this has led to a conundrum. Were galaxies aware of the environment they would end up in when they first formed, or did galaxies get transformed by their environment? What we call the nature versus nurture hypothesis of galaxy formation. Now, we now believe that galaxies can be transformed by the environment in which they sit. So, for an example, in a cluster, a spiral galaxy and its disk will have a harder time to survive the dense
Yeah,
region of a cluster, than it would do if it was in an isolated system. So the large-scale structure is a very important aspect of studying galaxies.
So, Professor Richard Ellis explained to us what is the role of bigger and bigger telescopes, ground-based and space-borne, to provide a better understanding of galaxies, their formation, their structure, their evolution, and its role in overall dynamics of the universe. We hope that in years to come, we'll have a much clearer picture of the problems, the puzzles that our current astronomers are facing, and new generation telescopes will provide better clues as regards these questions. Thank you very much, Professor Ellis.
Thank you.